Let's talk about the next topic, bottleneck management. Bottlenecks are a very important concept in operations management, and not only there. First thing to understand is, well, bottleneck, clearly that's a metaphor. We talk about a metaphor, right? And what does it stand for? What do we do with it? Why is it important? What implications do bottlenecks have for production management and control? Let's talk about these things. We know that a process step has a certain capacity, but also a process as a whole, the entire process has a certain capacity, because something goes in and something goes out, and we want to know how much goes in and goes out, and well, that follows certain rules and calculations and principles, and we can put a number to it. So if you look at this process that you see here, we've got 3 process steps: process step 1, process step 2, and process step 3. And the 3 process steps are carried out by 3 different stations: station A, station B, and station C. And each station takes a different amount of time to produce 1 unit. Station A takes 2 minutes to produce 1 unit, station B takes 4 minutes to produce 1 unit, and station 3 takes 3 minutes to produce 1 unit. Now, we have the process time for each station. But what is the process time for the entire process? What is the capacity of the entire process? What is the throughput of this process? Let's think about this. Now, the first thing to know is that process capacity and process time are inverse concepts. So if we have process time of a process step or of an entire process, then the process capacity, or the capacity of the process step, is the inverse of the capacity. So that's the first thing to know. The second thing to know is that the process capacity is the minimum of all individual resource capacities that we have in the process. So what is the lowest, which process step has the lowest capacity? Well, if capacity is the inverse of process time, then the station with the highest process time has the lowest capacity, which makes sense. The station with the shortest process time in this process is station A. It takes 2 minutes to produce 1 unit. If it takes 2 minutes to produce 1 unit, then we know we can produce 30 units per minute. The station with the longest process time in this process is station B. Station B takes 4 minutes to produce 1 unit. And if we know that it takes 4 minutes to produce 1 unit, we also know that we can produce 15 units per minute. Which means that station B determines the process capacity because it has the lowest individual capacity of the 3 process steps. Something else that's important to know is that the throughput of a process, or the flow rate, well, it can be determined by the capacity of one internal process step, but it could also be determined by some external constraint, by an external bottleneck. For instance, we may have a beautiful, perfectly designed, perfectly engineered factory, but there's no demand. So then the throughput in the factory is limited by demand. It's not limited by the capacity of the individual resources inside the factory. Similarly, there might be no supply. So for instance, at the moment, the Tesla plant in Berlin is not operating. And it's not operating because it doesn't receive the parts that it needs for production from its suppliers early enough. The reason being that some idiots shoot rockets at ships at the moment in the Red Sea, so that a large part of the ship traffic is being rerouted, and that takes, of course, much longer. So the parts are on the ships. Tesla doesn't receive the parts early enough, and there's a standstill at the Tesla plant. So the throughput at the Tesla plant is not determined by its individual capacity, not by the capacity of individual process steps, not by the demand, but it's currently determined by the availability of supply. So what we're seeing here is something that we've talked about before. There's a difference between capacity and performance, or between capacity and throughput is one performance measure. So capacity is what we can do. That's a maximum value, something that we could do if we lived in a perfect world, which we don't most of the time. And performance is what we actually do. So we talked about the traffic analogy earlier. Capacity is the maximum speed of your car, the maximum speed, but you rarely go at maximum speed. So the performance or the throughput, well, that is the actual speed that you drive. If you drive through Würzburg or through Schweinfurt and you drive 50 kilometers per hour, that's your performance. But you could theoretically drive 200 kilometers per hour. That is your capacity. So this brings us to the definition of bottlenecks. And what is a bottleneck? When you research a definition, you will find a multitude of different versions, multitude of different definitions. And it's important to realize that bottleneck first and foremost is a metaphor, right? I mentioned this before. And the term is used in everyday language and in a wide variety of scientific disciplines alike. And I've actually done quite a bit of research on bottlenecks. That was what my PhD project was about a couple of years back. And I created my own definition because I wasn't happy with what I found. So I'm defining a bottleneck as the element of a system, and that can be the node or the edge. So a node being, an object, and the edge being the connection between different objects, that limits the system in attaining higher throughput beyond a certain threshold. And, the threshold is important. That's important because that threshold is determined either by the bottleneck's physical throughput capacity, but that's rarely the case, or by organizational rules, or by operational practices. Let's talk about this in greater detail. You see this beautiful artwork here on the slide, and that's supposed to be a bottleneck. The bottle in this case is on the left, and the bottleneck is on the right. And you see this first arrow on the left that indicates the distance between the outer lines. That's the actual bottleneck. It's the physical bottleneck. It illustrates the physical bottleneck capacity. But as I said, normally we are not using our physical bottleneck capacity. Just like you're not normally driving your car at capacity. You're not normally driving at full speed, full throttle, because there are a number of different reasons that limit you from doing so. So part of the reasons why you're not driving full speed all the time is rules that we have for traffic. Our traffic rules prohibit you from driving too fast all the time. And it's the same in organizations. In organizations, we typically have all kinds of activities that people have to go through that limit the amount of work that can actually get done. There's, paperwork, for instance. But it's the same thing with working at machines, working in operations, working in picking in a warehouse, for instance. We talked about goods-to-person picking stations before, and so I assume you know what that is. So we build these hugely expensive goods-to-person systems where we free the picker from the necessity to walk around in the warehouse. So the picker can use presumably 100% of his time to pick, which can give him or her tremendous picking performance. Well, but we're not using our pickers very wisely in many goods-to-person stations. So I've seen companies spending millions on goods-to-person systems and on beautifully designed ergonomic goods-to-person stations. And then they make the picker do a lot of non-value adding tasks at the stations. And that reduces the picker's performance. They could actually pick much faster, but they cannot because they have to do a lot of stupid things like manual scanning of the totes, even though that could be done automatically, label printing, which could be done automatically, and so on. Right? So there is a lower amount of capacity that we can actually use. The effective bottleneck capacity, should the picking station be the bottleneck, is actually lower because of organizational rules. And then on top of that, we have operational inefficiency because, humans are flawed and also machines sometimes break down. So you have work to do and you could work very fast, but sometimes you've got to scratch your head or you're making a mistake and then you have to redo something. That is what I call operational inefficiency. So we could work faster, but, then life happens and we make mistakes and things like this. So the effective bottleneck capacity is the physical bottleneck capacity minus the capacity that we lose due to organizational rules and operational inefficiency. Let's talk about the term capacity for a brief moment. So what is capacity? Well, first thing we need to realize is that we have different types of production resources in most systems. And, economists, they talk about capital and labor. Well, labor, that's the people working in the system. And capital is, that's all the machines, the robots, conveyors, assembly lines, tools, whatever you find in a factory or in a warehouse. And, these two different types of resources, each of them has a certain capacity. These two different types of resources have a different degree of flexibility in the short term and in the long term. In the long term, basically all resources are flexible. If you know that your demand is going to grow and you have sufficient time to react, you could expand your production resources, for instance, by building a second factory. In the short term, however, flexibility is limited, at least the flexibility of capital, the flexibility of machines, of tools, of production equipment, because you cannot simply and quickly build a factory. This can take a long time. It can take months, if not years, to plan. It can take months, if not years, to build. So in the short term, we are somewhat flexible with labor, depending on the set of rules we have to work with, depending on the law, because also as far as Germany is concerned, we cannot simply hire and fire people for no good reason. That's not possible in Germany. In the US and in many other countries, it is possible. In Germany, it is not. And in many other European countries also, it is not possible. So there are limits to the flexibility of labor too. But generally speaking, labor is much more flexible than capital. And so, if more capacity is needed because demand turns out to be higher than expected, we may be able to react with labor. This is something that I hope you have discussed with Professor Machholz, or at least that was the expectation, that in the chapter on aggregate planning and S&OP, you discuss the various options that you have available to react, for instance, to demand surge. So if demand is higher than expected, you can hire more people relatively short term. And in the worst case, you can get them from an agency. You can get temp workers from an agency, which many retailers do, for instance, during peak times, Christmas or Black Week, for their warehouses. So Amazon, for instance, they hire thousands and thousands of people just for Christmas and just for Black Week. And then they get rid of them again. You can't do this with machines because the lead time to install them is way too high. And then for the rest of the year, you can't get rid of them. So then they are there. You've spent the money. And so capacity is inherently less flexible than labor. And again, there is a big difference between capacity and performance. So we sometimes talk about design capacity, which describes the maximum output that we can achieve. In theory, but almost always we cannot achieve the maximum output over any significant period of time. And that has a couple of reasons, and these reasons have to do with variability. Also, because of variability, in the moment we approach a very high degree of capacity utilization, so we try to get close to 100%, something happens. And what happens is that the work in progress inventory, basically the queue in front of the resource, the capacity utilization of which we're trying to maximize, the queue in front of that resource is growing. And actually it's growing to infinity as we approach 100%. And as you can imagine, if a queue grows in size, then also the cycle time grows in size, or the lead time actually grows in size, or in size, because we have waiting time. Any unit that waits in a queue accumulates waiting time. So as we approach high capacity utilization, we very often create extremely long lead times. And we talk about this in greater detail once we talk about queuing theory. Talking about lead time and process time. We've looked at this process before. This process consisting of 3 process steps. Now we need to distinguish the process time and the lead time from each other. The process time is, we talked about the process time for the entire process. We also talked about the process time for the individual stations. Now I've asked you, and I've answered the question myself because I'm on video and you're not there, but I've asked you, what is the station that limits the throughput in this process? And I have concluded it's station B, because station B takes the longest. It takes 4 minutes per unit. And so the inverse of the process time is capacity, and capacity in this case would be 15 units per minute, which is the lowest capacity among the 3 resources that we have available here. And 15 units per minute, that is the rate at which we can produce. It's a rate. Units per minute is a rate. And it's determined by the bottleneck process time that we find. So the rate at which the entire process can produce units is determined by the bottleneck station. It's determined by the bottleneck process time. Now let's distinguish this from the lead time. The lead time for this system is, think for a brief moment before I give you the answer. It's 9 minutes. If a product goes through the entire production process, it's being processed at station A, and that takes 2 minutes. It's being processed at station B, and that takes 4 minutes. And it's being processed at station C, and it takes 3 minutes. And the sum of these 3 process times is 9 minutes. So the situation is that we will produce exactly 1 unit every 4 minutes, because that is the rate at which we produce, but it takes 9 minutes in total to produce 1 unit. And this is without waiting time. We have no waiting time in this process, which is, of course, an idealized situation. Very often there will be waiting time in the process, so then the lead time would be longer. Let's have a look at this process, and let's think about the performance this process can achieve. So we've got a sandwich production line. You can think of this as a what is that? Subway, for instance, Subway or McDonald's or whatever you prefer. This is probably more akin to Subway. And we've got two identical sandwich lines here. There's one order point, so all customers order at the same point, and then some sandwiches will be processed by one assembly line and some other sandwiches will be processed by the second assembly line. And the process times at these assembly lines are identical. And in the end, there's one guy who wraps all sandwiches for both assembly lines and hands them over to the customer. Now, if we want to understand the performance of this process, first we need to understand the bottleneck station. We need to identify the bottleneck station of this process. So we want to look for the station with the lowest capacity or the longest process time, which is the same thing. And, intuitively you might say, well, the toaster, because the toaster has a process time of 40 seconds per sandwich. And that's true, the toaster does have a process time of 40 seconds per sandwich, but there are two toasters. So effectively, we can produce twice as many sandwiches, and that basically breaks down the rate to, or the process time to 20 seconds per sandwich. So then, if that is the case, the station with the longest process time is wrap deliver, which takes 37.5 seconds per sandwich. So now we have identified the bottleneck station, and we also know the bottleneck process time. Now, the bottleneck capacity is the inverse of the bottleneck process time. And not only the bottleneck capacity, but the capacity for the entire process is the inverse of the bottleneck process time. And if you convert the process time into a useful rate, you would end up at, I believe it is 96 sandwiches per hour. Now, you have to pay attention at the different time units. So here we've got seconds per sandwich, but for the process time, but it probably doesn't make sense to know how many sandwiches we produce per second. That's not a reasonable measure. But it would be good to understand how many sandwiches we produce either per minute, but perhaps even better per hour. So we take the inverse, which is 1 divided by 37.5, and then we multiply that with 3,600, because then we can convert the time unit second to the time unit hour. And it gives us sandwiches per hour, which is 96. Now, also, we want to understand how long does it take to produce a sandwich. Now, the throughput time for the entire process, well, that's the sum of all the individual process times of one assembly line, because any sandwich only goes through one assembly line. So we've got 30 seconds for order, 15 seconds for slicing the bread, 20 seconds for filling the bread, 40 seconds for toasting the sandwich, and then we've got 37.5 seconds. And the sum of that is the throughput time. And also, again, we don't have waiting time here, so this is an idealized situation, right? So normally we do have waiting time. Now, the example from the previous slide was simple in that it had two identical assembly lines for sandwiches. But what happens if we do not have identical assembly lines? Now, this is an example from a dentist. So you check in, you go to the reception, you tell them who you are, you give them your card, your insurance card. Then the first thing that happens might be that they take x-rays. And maybe that's a very American thing, because this illustration is from an American textbook. Anyway, they take x-rays while you're waiting for the dentist. And then the x-rays are being developed, and then one of two things happens. Well, either you go through the X-ray exam, or no, actually, that's not true. Both things happen in parallel. I apologize. So, two things happen in parallel. The X-ray is being examined by the dentist, and while the X-ray is being examined by the dentist, the hygienist is cleaning your teeth. And then, once the hygienist is finished with cleaning your teeth and the X-ray has been examined, you see the dentist, you talk to the dentist. He will tell you about the impression he got from the X-ray, and then you check out. Okay, so that's the entire process. Now, the first step is exactly the same as in the previous example. We try to identify the bottleneck. And the one process step with the longest process time in this example is the hygienist cleaning your teeth. This takes 24 minutes per patient, okay? So that's the bottleneck. And the bottleneck process time then is 24 minutes. The bottleneck capacity is the inverse of the bottleneck process time, so the inverse of 24 minutes. And the inverse of 24 minutes is 1 divided by 24, and then we multiply that with 60 because we would like to understand how many patients can be processed per hour, right? Per 60 minutes. And that would give us 2.5. So the capacity is 2.5 units per hour. Okay, now so far so good. So there has been no difference to the previous example that far. But now we have to think about the throughput time. How long does it take to go through the entire process? And this is where there is a difference to the previous example where the two assembly lines were identical. So here we have 2 minutes for the check-in. We have 2 minutes for taking the X-rays. We've got 4 minutes for developing the X-rays. And then the process splits up. And we have two things happening in parallel. On the one hand, we've got the X-ray examination. And on the other hand, we've got the hygienist cleaning your teeth. And then we've got these two processes emerge again. And then we've got the dentist, we've got the checkout. Now, in order to calculate the throughput time, the total process time without the waiting time of the process, you have to go through each path that is available, and then you have to identify the path that takes the longest. So in this example, the path that goes through hygienist cleaning takes the longest because that process step takes 24 minutes, whereas the examination of the X-ray takes only 5 minutes. So the examination of the X-ray will take place while the hygienist is cleaning. It's not delaying the process. So the throughput time for this process will be 2 minutes plus 2 minutes plus 4 minutes plus 24 minutes plus 8 minutes plus 6 minutes.